Hey everybody, welcome back. I hope you had a great lunch. I'm going to kick off this afternoon by telling you about research design meets market designs, and there's going to be a mix of some theory and applications. I just wanted to start off with a quick comment. I'm really thrilled to be here. Years ago, when I was a graduate student, I attended a summer school on market design, but that was a summer school that was entirely focused on economic theory. And as a sign of changing times in economics, it's great to see so much exciting work taking place in empirical aspects of market design. This is an area of economics where I think there's been a very fruitful dialogue between theory and empirical work over the last couple of decades. So, let me jump into it. So if you have any questions at any point, please interrupt me. Let's see how far we get with today's material. So up to now, in the last couple of days of the summer school, on the market design side, you've seen lectures focused on analyzing the theoretical properties of certain allocation mechanisms, and also what I'm going to call the allocated properties of certain matching mechanisms. So what do I mean by an allocated property? One way people judge the performance of a mechanism is by asking how many people got one of the choices that they wanted. How many medical doctors got their top choice, how many students got to go to their most preferred school, how many folks looking for public housing got one of their top 3 choices. And when we think about counterfactual questions, we often judge those based on these allocated dimensions. Now, another aspect of judging the performance of allocation systems is by asking questions about the productive dimensions of the assignment. For instance, does it matter if a medical resident gets their first choice in terms of their medical training? Do they become a better doctor? Okay. Does someone who got one of their choices in a public housing allocation system and got to move to a certain neighborhood actually get some labor market benefits of that allocation? Does a student who got assigned one of their most preferred choices learn more by attending the school that they wanted first, one of the most? And so this is kind of the theme for this afternoon's sessions. We want to think about how we would go about asking these questions about the productive dimensions or downstream consequences of assignment. And my portion today is going to focus on telling you some progress we've made on these questions. And I'm going to talk about 2 papers. Okay, so the broad theme of these papers is to think about resource allocation algorithms as experiment generators. Okay, so we think very carefully about allocating resources and rationing when there's not enough supply to meet the demand. And what's great about that is that there is some data exhaust that creates. There are these naturally occurring experiments that are a consequence of the fact that items are rationed. Okay, and so the papers I'm going to talk about today are together with Attila Abdulkadiroglu, Josh Angrist, and Yusuke Narita. And they fall into our thinking about this problem in a situation where we have some kind of lottery-based assignment. So there's some tie breaking that's based on a random number, and situations where we don't have lottery-based tie breaking. It's what we call non-lottery tie breaking. Right? Now, importantly, both of these are problems, are settings where we're thinking about static assignment. So we're particularly keen on looking at school placement. Doesn't matter if you got one of your desired choices, okay? Nikhil is going to talk a little bit about kind of dynamic aspects of these kinds of questions later today. Okay, so what's kind of our main idea? So I'm going to illustrate it first in terms of lottery-based tie breaking. So the deferred acceptance algorithm, Gale and Shapley's marvelous idea, satisfies a property that economic theorists call the equal treatment of equals property. Okay, so this is actually a concept that dates to Aristotle, but I think Shapley was the first person to introduce this in economics in his characterization of the Shapley value. What it simply means is if individuals have the same attributes, they should be treated equally. Okay, so this appears in problems of fair division. And for our context, equal treatment of equals means if we have 2 applicants who have the same exact preferences, and priorities. Okay, what I'm going to call a type. Type is your preferences, the choices of schools that you want, and your priorities at each of those schools. Then the mechanism must produce the same probability distribution over assignments. Okay, so two individuals who have the same type should get the same exact outcome. Okay, so equal treatment of equals is a big concept in mechanism design theory when we want to think about fair allocation. It's usually a reason why we think about using stochastic mechanisms rather than deterministic mechanisms. Okay. Now, equal treatment of equals may sound like something from econometrics, okay? And it's actually isomorphic to the idea of conditional independence, okay? And that's the opening for our approach here. So inside of deferred acceptance, when we have lottery-based tie breaking, if I have two applicants who have the same exact preferences and priorities, and we use lotteries to break ties to take those priorities and turn them into a strict ranking, what we have is a randomized trial. Okay, so two individuals who've applied to the same exact places with the same exact priorities are going to get the same exact probability distribution over outcomes, that is over allocations. But it's a somewhat complicated randomized trial because your odds of getting assigned depend on your preferences and they depend on your priorities. So it's a stratified randomized trial with a very high dimensional strata. And so our question really is how best to use these designs in service of asking what happens to someone after they've been assigned. Okay, depending on time, I'm going to show you about some applications of these methods to some particular questions in education economics. So our running application will be a study of charter schools in Denver. So Denver Public Schools is a fairly large district in Colorado. And what's really neat about Denver is it was one of the first districts to have all of the schools in the system, both the traditional public schools and the charter schools. The charter schools are somewhat autonomous, publicly funded schools where the teachers tend not to be part of the collective bargaining agreement. They all get assigned under a common process, okay, what they call unified enrollment. So we have some data from that Denver choice process. The other application I hope I'll get to is a study of the long-term effects of preschool in Boston, okay? In both of these studies, and we've done many other studies of this flavor, we're going to be using the stratified randomized trial embedded in the assignment algorithm to measure the causal effects of attending certain types of schools. And our main goal will be to try to eliminate the confounding generated by students who have different types, okay? So that's something I'm going to explain next. So let's define the problem. Okay, let's talk about what do I mean here. Okay, so you've seen a lot about market design, so I'm going to just jump into the research design side of the equation. So our goal is to extract ignorable assignment. Okay, so a little bit of notation now. So let's let DI of S indicate whether a student I is offered a seat at school S. Okay, so this is a 1, if the student is offered a seat, it's a 0 otherwise. Okay. Now in deferred acceptance and many other assignment algorithms, the only thing that determines whether a student gets an assignment are the inputs to the mechanism, right? So in deferred acceptance, that would be their preferences and their priorities. Once I know an applicant's preferences and priorities, I don't need to know their race. I don't need to know where they live. I don't need to know their free and reduced price lunch status to determine whether they get an assignment. All I need to know is their type, their preferences and priorities. Okay? Now, type, that is the schools that you ranked, the schools that you get neighborhood priority affects what you get mechanically through the algorithm, and it's potentially correlated with the outcomes of the assignment. So having an applicant's type might tell us something about the consequences of getting an offer at school S. Okay? So that's this challenge of omitted variables bias that we want to deal with. Now, what we could do is, as I said just a second ago, because deferred acceptance satisfies this equal treatment of equals property, I could look in my data set and I say, let's find everyone who's got the same exact type. I have a stratified randomized trial for those applicants, and I will just look at treatment control contrasts. Okay, what that means in terms of our notation here is, for any random variable W, So that's a variable that's independent of the lottery numbers of applicants. The conditional probability of being assigned to school S for applicant I, conditional on WI, so think of WI as race, and your type is equal to the conditional probability of being assigned school S, conditional on your type. Okay, this is just a mathematical version of what I just said. Once I know your preferences and priorities, your race doesn't determine what you get assigned, right? So this is true for any WI, so that includes pre-treatment characteristics, like whether you have a sibling at a school, and it also could include things like potential outcomes. Okay, so a strategy, a natural starting point is to just tabulate everyone who's got the same exact preferences and priorities and look at differences between students conditional on their type. Now, you might imagine that that's going to be challenging. Does anyone know why that's going to be challenging in practice? Any thoughts? Well, let's think about it this way. Suppose there's 10 schools, okay? Actually, where we are right now in Cambridge, Massachusetts has a choice process. There's roughly 10 elementary schools. Actually, Paolo, I think, talked a little bit about this, right? So how many possible ways are there to rank 10 choices on your choice form? Anyone remember?
10 factorial.
10 factorial. Fantastic, John, right? I'm teaching this to my son right now, right? First position, there's 10 choices. Second position, there's 9. Third position, there's 8, 10 factorial. Therefore, right? So that's a gigantic number, right? So if I want a condition on type, there's many different types to potentially condition on. Now, you might say, well, people are not going to consider all possible permutations, but still we have a very large number of potential types to condition on, right? And in fact, in the Denver application that I'm going to show you some numbers from, it turns out that full type conditioning is impractical, okay? So if we look at students in Denver who applied to a charter school, of the 5,000, roughly 5,000 applicants who applied to a charter school, there's 4,300 different types. Yes,
Is this also relevant if you do like kind of RD design on like, choice of major where there's like a bunch of majors and rank them?
Yeah, this is definitely relevant. So I'm actually going to get to that. So the way we're going to build up to that is we're going to first try to understand the lottery case. And then we're going to use our knowledge of that lottery case to get to the RD case. Yeah, exactly. So a quick answer where I'm headed is in the lottery case, we know what the lottery number distribution is coming from. We know that, typically it's drawn from a uniform distribution. In the RD case or the non-lottery case, more generally, we don't know what the distribution of tiebreakers is coming from, where the running variables are coming from. So we're going to have to figure out how to get around that problem. Okay, and that's why we're going to go local. Okay, so we'll definitely get to that. Okay, so full type conditioning turns out to be impractical in real life applications. Not that surprising given that theta, your type, is this very discrete object with many possibilities. So what we're going to do instead is condition on the propensity score. Okay, so what is the propensity score? So this is a concept that first found its life in studies of causal inference in observational settings. Okay, but here we actually have a randomized trial. Okay, so we're going to be deploying the propensity score in a somewhat different way. So first, what is the definition of the propensity score? That's simply the conditional probability of assignment given an applicant's type here. Okay, so the propensity score for assignment to school S is the probability that applicant I is assigned to school S, given that his type is theta. Okay, so again, DI is our indicator for assignment to school S. Okay, and what Rosenbaum and Rubin showed in 1983 is that if we go back to our conditional independence property, or our equal treatment of equals concept, then that property implies that for any WI that's independent of lottery numbers, think baseline characteristics or potential outcomes, the conditional probability of being assigned to school S, that is conditional on WI and the propensity score, is simply equal to the conditional probability of being assigned to school S, conditional on the propensity score, which in turn is just the propensity score. Okay, so I have to say this is a deceptively simple result. Okay, this is a very powerful result. Okay, but one way to think about what this result is teaching us is it's sufficient for us to condition on the propensity score. I don't need to condition on theta. I can just condition on a function of theta, okay? To deal with the omitted variables bias that's denoted here by WI notation. Okay, so why is this useful? Okay, so one reason this is useful is that we've taken this high dimensional theta object, preferences and priorities, and we've mapped it to a number between 0 and 1, right? Because it's a conditional probability, okay? So the score is going to be much coarser than theta because we might have applicants who have different values of theta, but have the same exact conditional probability of being assigned to a given school, okay? A simple example of that is, let's say I applied to school A and John applied to school B as his first choice, and then he applied to school A, but school B does not admit anyone named John. Okay, that's the priority at school B. Okay, then the fact that you applied to school B is irrelevant for whether you get assigned to school A. So if I looked at my data set, I would say, John and Parag, they're different. They have different thetas. But if we ask what's the propensity score for John and Parag at school A, we would find that it's the same. Okay, so that's the idea, and I'll show you another example of that in just a second. A second reason this is useful is when we can compute the propensity score, we're going to find the largest set of applicants who face a randomized school assignment experiment. Okay, so anyone who has a score, propensity score that's non-degenerate. So if your score is 0, that means you are not going to get into the school no matter what. Okay, if your score is 1, you're always going to get into the school. Okay, so there's no randomization in those two extreme cases. Those are the cases that we would call degenerate. So if I look at the values of the score that are in between 0 and 1, I have individuals who face some risk of getting assigned to a school. Okay. And then finally, the score is going to tell us something about the experimental design that's inside of deferred acceptance. Okay, that's going to teach us a little bit about where is random assignment coming from. Okay, well, I think we'll see the real dividend of knowing the actual formula. That's where I'm headed. Appears in the non-lottery, the RD case. Okay, great. So let's now illustrate some of these ideas in a couple of examples. Okay, so the first idea I want to illustrate is this idea that the score allows me to pool together individuals who look different. Okay, individuals who have different types. So here's my example. I have 5 students, 1, 2, 3, 4, 5, and there's 3 schools, A, B, and C. Okay, each school has 1 seat. Okay, and my table of preferences is given on the slide here. So whenever I see these tables, I remember being a student and these numbers going by way too fast. How do I make any sense of this? What I always like to do is look at where there's some conflict. Okay, who's kind of competing with who in terms of their choices. And so here there's real conflict between the first 3 students. Why? Because they all want school A as their first choice, right? There's only 1 seat at school A, so only one of them can actually get it, okay? The other source of conflict here is between students 4 and 5. They both want school C as their first choice. Okay, that's what's going to be important for us in the preference table here. Now, what about the priority side? In the priority side, we'll say student 2 has priority at school B, and student 5 has student 5 has priority at school C. This is why these examples are sometimes hard to talk about when you confuse who's a student and who's a school, right? Okay, so let's think about what happens with deferred acceptance. So under deferred acceptance, okay, well, you'd say, I got this data set. This is what it looks like. Why don't I do full type conditioning? Okay, that natural starting point. Well, I'm in trouble already because every single type here is different. Okay, so just looking at the preferences, the only choice would be applicant 1 and applicant 2, but you know they have the same preferences, they don't have the same priorities, right? Because applicant 2 has priority at B and applicant 1 does not. Okay, so why is the propensity score useful? Okay, well, under deferred acceptance, what's going to happen? Well, let's start with applicant 5. Okay, so applicant 5 wants C, In the algorithm, they're going to propose to C. And now applicant 5 has priority at school C, so there's no one who can dislodge them at C. So when applicant 4 comes along and also proposes to C, there's no way applicant 4 will get C. Okay? So de facto, we're back to the situation that we just talked about where applicant 4 is like John and he's applied to school C and school C says, sorry, you don't have priority here, you're never going to get it. Okay? So we can essentially ignore the fact that John has listed school C as his first choice and then observe that the first 4 applicants de facto have listed A as their top choice. And since no one has priority at A, the lottery number will determine who gets an assignment at A. And since there's 4 students, each student will get assigned to school A with probability 1/4. Okay, so if we're interested in the propensity score at school A, we now can pool together 4 different students. Okay, they all have the same propensity score. Okay, so that's kind of fact number 1. The score allows for pooling. Okay, now let's take a look at another example. Okay, so here's an example that's even a little bit simpler than our first example, but it illustrates a second point. Okay, so in this example, we have 4 students, 1, 2, 3, and 4, and 3 schools. Okay, and each has 1 seat and no priorities. The preferences of the students are all different. And now I said, let's take a look at where there's conflict. So students 1 and 2 both want school C, but student 3 wants B and student 4 wants A. Okay, so there's conflict over C. But there's something interesting about this example. Let's say student 2 doesn't get C. Okay, let's say they get outcompeted by student 1. Then the competition will turn to B, because the student 2 and student 3 are both competing for B. Okay? And let's then imagine student 2 loses that competition at B. It kind of trickles down, okay? And student 2 would then apply to A and would be competing with student 4 for A. Okay? So types are unique here. Now, how am I going to compute the propensity score in this example? Okay, so here's another quiz question. Okay, so one way I could do it is by enumerating all possible lottery draws. Okay, so how many possible lottery draws do we have with 4 kids? Here's a hint. John was on the right track, okay, with his previous answer. Anyone want to help me out? 4 factorial, right? The factorial comes back, right? There's 4 ways to be in the first position. There's 3 ways to be in the second position, 2 in the third, and 1 in the fourth. So 4 factorial is 24 possible assignments. Not as bad as 10 factorial, but still a little bit of a pain in the neck to actually compute, right? And so we have gone through and computed the 24 possible assignments. And when you do that, what do you see? What you see is that the probability that an applicant of type 1 is assigned to school A is 0. Okay, that's easy, right? Because the applicant's not even listing A, right? So there's no way they're going to be assigned A. The probability that an applicant of type 2 is assigned to A is going to be 2 out of 24. 2 out of the 24 lottery numbers, they'll get assigned to A. Can anyone give me a lottery number where that happens? Does anyone see which of the 2 possible lottery draws are going to be ones where applicant 2 gets assigned to A? Well, applicant 2 can't be first in the draw, right? Because they'll get C, right? So what would be a lottery realization where applicant 2 gets assigned A? Anyone want to try? Okay. Yeah, please, yeah. 1, 3.
Where a lower number is high priority.
Yeah. Okay, so first is 1, and then who's next?
Next is 3.
3. Okay, great.
Then is 2.
Then is 2.
Then is 4.
Perfect. Okay, so can you tell me why that works? Why would applicant A get? Applicant 2 get A in that case?
Because then applicant 2 doesn't get C because 1 gets C.
Yeah.
And then applicant 2 doesn't get B because 3 gets B.
Yep.
And then the competition is only between 2 and 4.
Yep.
And we want 2 to win, so.
Beautiful. That's exactly right. So that's one of the 24, right? And we could also compute the other by just swapping the role of 1 and 3. Okay. So the reason why I wanted to kind of belabor this point and go through the mechanics here is what you see is your odds of getting assigned a given school depend on what happened to you in the algorithm at higher ranked choices. Okay. For our applicant to get assigned at school A, probably the case that that applicant did not have a great lottery number, right? Because they lost out at C and they also lost out at B, okay? So the information that we have to keep track of, okay, and we're going to be much more formal about this, is the information about what schools you got rejected from, okay? And how hard was it to get into those schools? Okay, so that's for applicant 2. I won't go through applicant 3 and applicant 4. You can do that at home if you wish. But we're still stuck here because in this example, what you see is that all 4 of our applicants have a different value of the propensity score. Okay, so there is no pooling here. We don't get the benefit that we saw in the first example. So what are we going to do? Okay, so you could say, well, there's no comparisons that we can exploit here. But let me show you something next. Okay, so this is just some more details on that example. So I'll skip ahead. What I want to do is turn to something that you guys saw with Irene Lowe's lecture, which is thinking about going large. Okay, so this is a common device in economic theory and econometrics. What happens when we take a given problem and try to think about an asymptotic limit? Okay, and the type of limit I want to take is a what's called a replication. So let's take example 2. There are 4 different types of preferences, and let's just make a copy of each of those. Okay, so we'll call a 2 replication an economy where we have 2 applicants of type 1, 2 of type 2, 2 of type 3, and 2 of type 4. Okay. Likewise, a 4 economy or an N economy is going to be one where we have N of each of the 4 types of applicants. Okay, so this is an idea that goes way back in economics to DeBrew and Scarf, maybe even before then. Okay, and this is very useful because we can maybe make some more analytical progress on what happens in these kinds of situations. Okay, so what we've done in this example here is we said, let's figure out the probability of assignment to school A as we replicate the economy, as we have more and more applicants of a given type. And something kind of miraculous emerges when we do this. Take a look at the applicant of type 2 and the applicant of type 3. So we know that when N is equal to 1, applicant of type 3 has a 1/24th probability, and the applicant of type 2 has a 2/24th or 1/12th probability of assignment to A. But when I replicate this economy, when I have more and more copies of the agents, the conditional probability of being assigned to school A ends up converging relatively rapidly, okay, to the same value between applicant of type 2 and applicant of type 3. And so you might think that if we had realistic data sets where we have applicants, we have a large number of applicants, we could appeal to the continuum idea that Irene talked about to get some more traction on the score, okay? And so that's where I want to turn to next, okay? So I'm gonna work with the continuum model of deferred acceptance that Irene talked about and give you a formula for the deferred acceptance propensity score, what we call the DA score, okay? Okay, so again, why am I doing this? Okay, why do I want a formula? Well, my goal is to give you the propensity score for an applicant of type theta. What is the probability that they're assigned to school S? And that's going to be generated by the permutation distribution. Okay, repeatedly draw lottery numbers. Okay, in Denver, that would be 26,000 factorial possible lotteries. Okay, so there are 5,000 charter apps with 26,000 total apps. And now, of course, you could say, I don't have to draw all 26,000 factorial lotteries. The law of large numbers tells us it's enough just to sample from lotteries. But since the covariates here are discrete, the thetas, the preferences and priorities, the resulting estimated propensity score will have as many points of support as the underlying theta, okay? And now simulation scores are also a black box, okay? So we have to figure out, do we want to smooth this or not? This is a possibility, okay? When we have lottery-based tie-breaking, one could always do this and go down that path. I don't want to do that here, okay? What I want to do instead is give you a formula for the propensity score, okay? And the challenge here is that, except in very special cases, we already saw in example 2, the propensity score has no real closed form, right? It's just, you know, example 2 is just still 4 kids. Imagine more realistic scenarios. So that's my motivation for thinking a bit about this large market model. Okay, where we're headed is the formula that I'm going to give you is going to give you the DA score as a function of a few statistics. Okay, so I don't need to know everything about your preferences to compute the DA score and everything else going on in the market. I can give you a formula for the DA score that depends simply on a somewhat elaborate set of cutoffs in the economy, okay? The second dividend that we'll see from the DA score is I give you a formula. It's justified in this continuum economy, okay? It's exactly correct in that economy. So if I want to apply it in a finite economy, you can think of our formula as giving you a formula that you don't have to smooth or round or do any kind of simulation. And then finally, as I mentioned, the score will tell us, you know, why schools have random assignment. Okay, and I'm going to show you an example there because that's something that's quite surprising. So let's now get into a little bit of notation. Okay, so the goal here is I want to give you the DA score. Okay, and I want to introduce one really key concept, okay? And to do that, I need to introduce a couple of pieces of notation, okay? So we have an economy where there's I students and they have preferences and priorities. I'll just call the priorities numbers, okay? So this is like you have sibling status at a school, you live in the walk zone at the school. A priority of infinity is the way to encode that you're ineligible at the school, okay? So now a student's type is just a collection of their preferences and priorities, okay? When I have row sub I, that's your priority at school 1, at school 2, at school 3, so on and so forth. That's on the demand side. On the supply side, we have S schools, capital S schools, each with a capacity QS, okay? And in the continuum, you can think of our set of students as an interval and QS as a proportion of the interval that can be seated at school S. A student's random lottery number, RI, we'll assume here is IID uniform on 0, 1. And a student's rank at a school will simply be their priority at the school. So again, priority is row IS here. So kid I's priority at school S, that's an integer. Okay, so maybe you think sibling is priority 1. And then we will add your lottery number. Okay, in fact, this is how Cambridge does this in their files, right? I think Paulo, right? The data file you guys add, right? They take your priority, it's an integer, and then they add a big number, a decimal number for lottery numbers. Okay, so that's what I'm going to call student's rank. Okay, and we've seen earlier in this week that we can think about deferred acceptance assignment in terms of cutoffs. Okay, so a student will be assigned to school S if their rank, that is their pi IS, is less than or equal to the cutoff at school S, right? So I cleared the cutoff. And for any school that I like better than S, okay, for any S tilde that I prefer to S, I didn't clear the cutoff. Okay, so basically I didn't get any higher rank choices. I got to a school where I cleared the cutoff, okay? And so that's a characterization, that's a way of describing what deferred acceptance is going to produce. What's important for us is the lottery number. Where does the lottery number matter? It matters for assignment to school S only in what I'm going to call the marginal priority group. Okay, so let me just illustrate that in an example. Okay, again, imagine this is your data set. Okay, we're looking at a given school. I've sorted the applicants at this school based on their rank. Okay, so that's in the first column here. The first kid here has a priority of 1. Remember, that's the integer. The lottery numbers we've scaled to be between 0 and 1. So their lottery number is 0.13. So their rank is just 1 plus 0.13 or 1.13. And that kid gets an offer. Okay, we continue with the sort, right? The next kid is 199, and then we go to the second priority group. And in the second priority group, we have a cell where some kids got an offer and some kids did not, right? So the first two kids here got an offer and the second two kids did not. And so this is what I'll call a marginal priority group. It's the priority group where there was some rationing. Some kids got in and some kids did not, okay? Anyone who's in the last priority group 3, is not getting an offer. So that's why the offer is equal to 0, okay? So our notation here is your marginal priority is simply going to be take the cutoff. Okay, so the cutoff is defined here as the last kid. Oops, that's the point, right? So the cutoff here is the last kid to get an offer at the school. So that's 2.35. The marginal priority is what is the priority of that kid? Okay, so he's in priority group 2. And what's the lottery cutoff? It's 0.35. Okay. Okay, so this is the terminology and the notation here. Okay, so in this example, this is actually a little bit simplified because I'm looking at all the kids who are getting an offer at this school. Now, in principle, what could happen is there could be, let's say, kid 199. You might actually find a 0 for that kid. Okay. How could that be? You'd say when we did the sort order, his rank was 199. It's greater than 205. How could it be that kid 199 got a 0? Well, the answer is it could be that that kid actually got into a higher rank choice. Okay, so this example is somewhat stylized. I'm assuming, for instance, this is everyone's first choice. Okay, so that's why we see this very nice structure. Okay, great. Okay, so that's the marginal priority concept. Now, a couple of more slides of notation, and then we'll turn to some of the empirical work. So how am I going to give you a formula for the score? Let's take this applicants who've listed school S and call them capital theta S. Okay. Now, I just mentioned that it's going to be very important to think about the schools that you didn't get into. Those are the schools that you had wanted to go to ahead of school S. So let's denote that set as the better than set, or B of theta S. Okay, so B of theta S is the upper contour set, you could say, the set of schools that type theta prefers to school S. Okay, so take my applicants who listed school S, and I'm going to partition this set into 3 groups. Okay, the first group I'll call theta SN. These are applicants whose priority is worse than the marginal priority at the school. Okay. So why theta SN? Well, these are applicants we'll call never seated. Okay, these are applicants who have worse than marginal priority at school S. Okay, so in the table here, that's these guys at the bottom here, right? They're worse than marginal. They're never going to get a seat at school S. Okay, no one in this seat gets a seat at school S. Okay, the other partition is going to be denoted as theta SA. Okay, these are individuals that we'll call always seated. Okay. So these are applicants, okay, whose priority is always better than, always better than the marginal priority. Theta, rho theta S is less than rho S. Okay, so back to our table here. These are the applicants here in priority group 1. Okay, they're always seated. If I were to redraw the lottery numbers, they would always get a seat at the school. Okay. Now, the last group, okay, is the group that maybe is the most intuitive group. That's the group where there's some rationing. Okay. This group is a group that we call the conditionally seated. Okay, so this is a paper with Josh Angris. You might have gotten the never takers, always takers, and compliers. So that's where the NAC is really coming from, you could say, even though it's a totally different concept. Okay, so theta C are those who are in the marginal priority group. Okay, so that's this group back here, priority group 2 here. Okay, you're going to get assigned a seat at school S if you clear the lottery cutoff and you didn't get a higher ranked school. Okay, great. Okay, so that is our partition of sets. Now, when I give you a formula for the score, it'll depend on what set you're in. Are you an always taker, always seated, never seated, or conditionally seated? Okay. Now, the last piece of notation, okay, and the hardest one, okay, is this concept that we call the most informative disqualification. Okay. Now let me try to explain this intuitively, and then just give you the idea of what this notation is trying to take into account. If you go back to our example 2, I made the point that in that example, whether a kid gets assigned school A depends on what happened to that kid at their higher rank choices. Okay, so in the course of the algorithm, there is some truncation or censoring of your lottery number that occurs if you got rejected from a higher rank choice and applied to school A. Okay, so again, let's say John has ranked school A first and I've ranked school A 10th. Okay, I'd only get to apply to school A if I've been rejected from my 1st through 9th choices. Okay, so intuitively, when would that happen? That would happen if my lottery number was really lousy, right? I didn't get into my 1st choice, I didn't get into my 2nd choice, I didn't get into my 3rd choice, so on and so forth. So by the time I get to my 10th choice, when I propose to school A, you can infer that I probably have an adversely selected lottery number. Okay? So that's this idea of an informative disqualification. Okay, what has happened to the choices above the school that you are applying to and trying to think about the propensity score. Now, what about the word most here? Okay, so let's think about another example where we have 2 applicants who both listed school A. And it turns out that the schools that the first applicant has listed ahead of A include a school that was really easy to get into. Okay, so that's our first applicant. There's a school X that's really easy to get into. Our second applicant has applied to X ahead of A, and they've also applied to Y ahead of A. Okay, now imagine that X was really easy to get into and Y was not so easy to get into. Okay, well, what's important for when we think about applications to A? What's important is what's happened to the censoring or truncation of your lottery number at the point that you got to apply to school A. And if our second applicant applied to X and Y, and we said X is the easiest school to get into listed above A, the fact that he got rejected from Y tells us nothing about his lottery number, because we know he was rejected from X and almost everyone got into X, okay? So that applicant's most informative disqualification, look at all the choices above A, what was the easiest school to get into ahead of A? It turns out to be X. And if that turns out to be the same as our first applicant who just listed X ahead of A, then they would share this most informative disqualification. Okay, so that's the idea here. Okay, so now let me just quickly tell you about this. So what is the mid doing? It's telling us how the lottery number distribution is truncated by qualification at more preferred schools. Okay, how censored is the lottery number distribution? Okay, so there's 3 cases here. Okay, the first case is there's no truncation at all. The mid is equal to 0. And that occurs, for instance, when we're thinking about a school you listed first. If I listed that school first, there's no way for my lottery number to be truncated by the time I apply to the school, right? Because I didn't get rejected from any other place. More generally, the mid is equal to 0 when the priority status is worse than marginal at all higher ranked schools. Okay, so I'm in that bottom bucket, priority group 3 in our example, at all of my higher ranked schools. So I had no shot of getting into those schools. So there'd be no truncation. Go back to the example where John applied to a school that does not admit anyone named John, right? There'd be no truncation from the fact that he got rejected from that school, right? Because there was no way he could get into that school. Okay. Second example, second case is when our most informative disqualification is equal to 1, okay? This is the situation where there's complete truncation, okay? So what does that mean? That means that the schools that I like better than school S, so that's what that B set is again, B of theta S, those schools include a school where I get in for sure, okay? So let's say school A is my 10th choice and another school is my first choice, and I'm a guaranteed applicant at my first choice, then I'm completely truncated. So my mid would be exactly equal to 1 from the point of view of my 10th choice, school A. All right, so that's the 2 easy cases. Okay, now the last case, okay, what that notation is telling us is it's got a max in front of it, okay? So the max is telling us what was the highest cutoff at a school where you are in the marginal priority group. Okay, so max of the lottery cutoff tau s, given that you're in the marginal priority group, that's what rho of theta s is equal to rho of s, for a school that you prefer to school S. Okay, so mechanically what this is simply saying is, look at your applicant, look at all the cutoffs of the schools above where you applied, look at where you're in the marginal priority group and pick the most easy to get into school, and that will be your most informative disqualification, okay? And so these are our three cases, and now we are ready to give you a formula, okay? So that's basically it in terms of the notation. So I can now explain what the DA propensity score is in the continuum economy. Okay, so I now have a handle on the conditional probability that an applicant of type theta is assigned to school S. Okay, there's these three cases. The first case is you're never assigned, right? So you're in the never seeded group. So your propensity score is 0. You didn't even list the school, right? The second case is you're in the always seeded group. Okay, so here your propensity score is not equal to 1. Okay, now here is a kind of maybe first dividend with this formula. You might have thought if I'm always seeded, I should get a propensity score of 1. After all, I'm always seeded. Okay, but what we have is a term that's a little bit different than 1. We have 1 minus mid. Okay, what that's teaching us is that there is still some rationing happening by virtue of not getting into a higher rank choice. It is true that by the time you apply to school S, you'll get in for sure. You could be a guaranteed applicant there, right? Okay, but your opportunity to apply to school S could be determined randomly. In fact, it could be determined by getting rejected from a higher rank choice randomly, okay? So your probability of being assigned there is, let's find that truncation point, the mid, and just take 1 minus the mid, okay? So that's the second case here, okay? Now, one interesting dividend with this here in terms of your data set is you might look at your data and say, do we have an experiment at the school? Was there actually rationing at this school? Okay, and you look at the school and you say, well, there's 100 seats at the school and 80 kids were offered a seat at the school. So by most conventional definitions, you'd say that school wasn't oversubscribed. They had 100 seats. The supply was 100. Only 80 kids got offered a seat. So if another kid came in, they would get into the school for sure, right? So unfortunately, we don't have a random experiment at that school. You might think, but that would be completely wrong, right? The reason it's wrong is some of the 80 kids who got offered a seat at that school could have been randomly assigned to that school by virtue of being rejected randomly from a higher ranked choice, okay? So that's kind of the first thing that we're gonna look for in the data. How much more power do we get to extract these experiments by looking at these higher ranked rejections, okay? So that's the second case. Now, what's the third case? The third case is taking that higher rank rejection probability, the 1 minus mid, and multiplying it by the renormalized probability of getting assigned school S when you're conditionally seeded. Okay, so you're in the marginal priority group at school S. We know that your lottery number is, between mid and 1. Okay, so the range here is just 1 minus mid. That's why that's in the denominator. And the cutoff at the school is tau S. Okay, so the length of the interval is tau S to the mid. And so the probability is just tau S minus mid divided by 1 minus mid. Okay. Okay, so this is the formula. Okay, so now this is a result about the continuum economy. In some of the papers, some of the details here, we have results showing that if I compute the sample analog of this, it'll converge uniformly to the finite market score, okay, as the market grows. Okay, so what's nice is I can kind of operationalize this, right? I go to my data set, I go to every school, compute what the cutoffs are, I go to every applicant theta, compute what the mids are, and just plug away, right? I'm in shape, okay? And so that's what I'll show you next. Okay, so we can estimate the DA score simply by putting students into these groups, never seeded, always seeded, and conditionally seeded, figure out what the hatted, the empirical cutoffs are, lottery cutoff tau S, and the mids. And so that's what I'll show you some results for. Let me skip the frequency. Now, in the back of your mind, you might be saying, well, why did we need to go through all of this headache? Couldn't I have just set the machine running on my computer and drawn many, many lottery numbers, right, and done some kind of smoothing, okay, pooling together of, very close probabilities, and you could, okay? So again, the real dividend of this is going to be shown when we go to the non-lottery case. When we did this in Denver, for instance, we took 1 million lottery draws. We ran deferred acceptance 1 million times. We looked at, for each theta, what is your conditional probability of being assigned a given school? There was no dimension reduction, so we had to do some smoothing. So there were a total of 1,148 score values for about 1,500 applicants who had non-degenerate risk of assignment to a charter school, so risk between 0 and 1. Okay, so there's some smoothing that one would need to think about. Okay, great. Okay, so now let's turn to the application here. Okay, so our application is using data from Denver's school choice match. Okay, now Denver, I mentioned in 2012, there were 2 cities in the US that brought together the charter sector and the traditional public school sector and said, let's have a unified application system. Denver was one and New Orleans was the other. And what we're going to try to do is simply ask, what is the effect of attending a charter school? Okay, so the way I'm going to do this, let's define any charter offer dummy. Okay, so previously I had defined the score for a given school S. Now what I'm going to do is think about assignment to any charter. Okay, so what I'm doing is asking, did you get assigned to any school S that is a charter school? Okay, so that's simply the sum of all of the individual charter school offers. Okay, so I just can simply collapse that down, aggregate that up. The any charter propensity score is going to just be the sum of my individual school propensity scores for the schools that are charter schools. Okay, and we'll let CI indicate any charter enrollment. Okay, so I'm going to show you some results from the following 2-stage least square system. Okay, so what's my notation here? Right, so again, CI is any charter enrollment. I have my any charter offer dummy DI. Okay, and then I have this set of controls. Okay, so I have dummies for each propensity score value. Okay, and those dummies are indexed by X. And then we have a similar setup for the second stage. Okay? Now, one thing to note here is I gave you a result for a single school here. So I'm doing some aggregation here, right? So I am giving you a weighted average across different score values. I'm doing that marginalization using 2-stage least squares. You might ask, well, why do you need to aggregate like this? Why don't you tell me the estimate for every single school? Okay, and that's a great question. That's something that we're actually working on. The answer to the question why we don't do that is it's very imprecise. Okay, if you try to disaggregate this too far, your estimates get pretty noisy. Okay, so great. Was there a question? Yeah, Nikhil. Yeah.
Also, is there a way to link the local average effect that comes out of this 2-stage squares with the, maybe you're going to do this in a minute, but like what's the estimate from this 2-stage squares and how do I interpret it in addition to just the aggregation across schools? There's some set of students, right?
Yeah. So this is definitely a local effect in several respects. So I'm only able to do this for students who are part of a school assignment experiment, right? So those are students who have non-degenerate risk, right? So so that's a subset of students. In the paper, it turns out in Denver, because it's a unified enrollment system, the types of kids who face risk look very similar to the types of kids who actually enroll in a charter school. If you go to like a city like Boston, which has a separate process for applying to charter schools, it's much more frictional. You have to go to the school and apply. In recent years, they have a common application, but it's a very self-selected pool. But at least in terms of their observable characteristics in Denver, it's very similar. And I think that's because of the unified application. Now, there are formulas for exactly the weighted averaging that I'm doing here. This is, with 2-stage least squares. I'll show you something that we do this a little bit more flexibly. It turns out not to matter much in practice. In the paper, we try to disaggregate this somewhat to look at just how much heterogeneity there is. So one type of disaggregation people in the literature on charter schools talk about is charter schools that are run by charter management organizations. So these are like professionalized organizations that run charter schools. The most famous example is KIPP. And then you have what people call mom and pop charters. Okay, this is like Nikhil, you and I say, let's run a charter school on dynamic structural econometrics, okay, for the city of Boston, right? And what the literature tends to find is those types of charter schools are not very effective. Okay? And that's what we also find here. That's as far as we got in terms of getting estimates that are not just totally noise. Now, another thing just kind of related to the themes of this summer school is you might be asking, okay, well, this is really local. We're interested in counterfactual questions in this summer school, right? So how would we go about getting to those counterfactual questions, right? So the way I think about this is we're at the stage where we're trying to understand what is the effect of getting one of your choices, right? Now, some of the papers you saw earlier this week are asking about, what choices you would get under different allocation systems, right? So this kind of evidence from this strategy should feed into evidence from the choice modeling and looking at these different counterfactual allocations if we want to judge those counterfactual allocations on their productive dimensions. Okay, so there's now a handful of papers that do this. I think this is a very exciting direction. So we had Chris Walters, his thesis did something like this, where he linked the local average treatment effect to choice equations and asked counterfactual questions. So there's tons of work to do. Nikhil's going to talk more about that too. Exactly. Okay, great. So let me just show you a couple of things. Okay, just in terms of the data. So the first thing is, okay, all this terrible notation. Why did you drag me through this? Well, one reason is to show you just how much of a sample size gain we get. So until we started doing this work, people had looked at these centralized choice algorithms as experiment generators, and they usually just focused on people who applied to a school first. And they said, we're going to compare people who ranked a school first. Some got an offer, some did not. So that is what we call the first choice research design. Okay. Now you might think, there's something unusual about the folks who ranked a school first. What this figure is showing is what do you get in terms of number of students who are subject to randomization if you move beyond the first choice, okay? If you go and compute the propensity score. This is for all of the non-charter schools in Denver. We have a similar figure for the charter schools. And the way to read this is each point here is a school, okay? It's ordered by the school's capacity. This is a log scale capacity on the x-axis. The dot is the number of first choice applicants subject to randomization, okay? So any dot here that's at 0 means we didn't have an experiment when we focused on first choices. And the arrows here indicate the number of additional applicants subject to randomization when we think about the entire choice that they submit, which we now can use the propensity score formula. Okay, so this is something that's promising in terms of getting more precise estimates. Let me show you another thing, just a bit about the formula I gave you. How does it actually work? Okay, so I said one thing we can learn is where is the random assignment coming from? Okay, so I've taken the propensity score for Strive charter school. Okay, so this is a pretty well-known charter school in Denver. They have 6 different campuses. The GVR is Green Valley Ranch, all the way down to Westwood, okay? And what I've done is I've taken every applicant here. So at Strive Green Valley Ranch, there's 324 eligible applicants. The capacity is 147. And the number of offers at the school is 112, okay? So this is a place where you might say, there's no way we have an experiment here, right? 112 people got an offer. The capacity was 147. So if another kid came along, they might have been able to get an offer, right? And indeed, what you see is that's not right? Because we have an experiment here. So the deferred acceptance score in column 8 is 116. So the number of applicants who have a non-degenerate chance of being assigned to Strive GVR is 116. And why is it 116? Well, it turns out, okay, that all of those applicants are in the theta A set. Okay, what does that mean? That means in the algorithm, when they got to apply to Strive GVR, they get in for sure. Okay, that's what we would expect. After all, the capacity was 147, and they made a total of 112 offers. Okay, but the opportunity to apply to Strive GVR was randomly determined by a higher ranked rejection. Okay, so these are the applicants that we've discovered using this formula. The higher ranked rejections generate random assignment at Strive GVR. Okay, and it turns out that this is not trivial. We have a fair amount of that here at Lake and Highland and Montbello as well. I think the more conventional random assignment you might have expected is, at Westwood, right? So 238 applicants are in the conditionally seeded group, in the marginal priority group, and they haven't been censored. Their mid is less than the lottery cutoff. So that's kind of where I would have started and said, well, this is where our experiment was, but we would then be missing out on these other experiments. Okay, so now how, kind of what's the bottom line? Okay, what are our estimates from this two-stage least square setup? So let's just focus here on column 3 and column 4. Okay, so I'm showing you estimates, per year estimates of charter effects. Strive and all of the other charters in Denver are incredibly effective. Okay, so the estimates here are reported in standard deviation units. The opportunity to go to a charter school, and if we look at the effect of enrolling at a charter school on math in Denver, increases your standardized test scores by 0.5 standard deviations. Okay, so 15 years ago, before you did charter schools research, no one would ever believe you had any educational intervention that had a 0.5 standard deviation effect. Okay, you would say you had a mistake in your data set. It's impossible to do something like that. Okay, and this is a pattern that we tend to see in big urban districts where schools like Strive tend to be quite effective on standardized tests. Okay, so this is from the two-stage least square system. There's other ways of weighting effects across values of the propensity score that give similar estimates. So that's shown in column 4. Let me just skip that and show you one other thing before we move to the non-lottery case. Okay, so let's say we were to approach this question without having knowledge of the propensity score. One thing you could do is go back to the first choice strategy. Okay, so we rerun the machinery, okay, just acting like the analysts would have acted prior to this work. And what you see for math is actually the estimate is a little bit larger. Okay, those are not statistically different, but look at column 2, panel B, the math estimate here, okay, that's 0.596. Okay, so incredibly large effects on math. And here you might say, well, those are people who listed the school first, so maybe they were unusually primed to benefit from attending that school. And when we turn to column 1, looking at people who are randomly assigned to that school for any of their choices, it's that 0.496 I just showed you. Now, the proof of the pudding here is our precision gain. Okay, so what is the standard error of these two different estimates? So if I just use my first choice research design, my standard error is 0.1 compared to 0.07. So you can convert that into something maybe that's a little bit easier to digest. What would be the sample size increase for an equivalent gain between column 2 and column 1? Okay, so if I use the first choice strategy and I compared it to using the full DA score strategy, it's as if I had twice the amount of data. Okay, so that's maybe a reason to embrace the details here. Okay. Okay, so let me pause here. If there's any questions, yeah.
So just in terms of interpretation, this result seems, because the charter schools are not full, right? So there's some of them with spare capacity at the end of the day. And if the benefit of having going to one of these schools is have a standard deviation, that almost kind of implies are like parents not like optimally choosing schools for their kids, like in terms of the broader population, or how would you think about that?
That's a very good question. It's actually, Nikhil, did you talk about this? Okay, Nikhil's going to do that next. So now that we have some measures of the productive dimensions of assignment, we can ask exactly that question, right? How does that relate to the demand for schools? There is work I would say there's a kind of active debate on this very topic. So I have a paper from a couple of years ago asking, do parents demand effective schools? And part of the strategy of that paper is to take estimates of school effectiveness and relate it to school demand. Okay, and what we argue in that paper is that if I try to predict whether you apply to a school based on its effectiveness, as defined by how much you would learn from attending that school, and compared to predicting the demand based on the peer mix at the school, so what is the demographic attributes of your classmates, it loads almost exclusively on the peer mix at the school. Okay, so that would support the idea that maybe parents are not demanding schools that are effective. What they're demanding are peers. Okay,
We'll see that later.
yeah, so that's coming here. You know, I think it's a fantastic question. I love that question. There's many examples where we have oversubscribed educational programs, sometimes using centralized allocation systems that reduce achievement. So that's kind of the flip side of what we just saw here. So here we saw a school that's really effective that still has seats left over. Why aren't people taking those seats, right? And you know, one reason could be they don't know. It could be there's things beyond these test scores that families care about, like proximity or safety. Or now the flip side question is, well, if you look, for instance, at charter schools in Massachusetts in the suburbs, they tend to be oversubscribed. Okay, and if you look at the effect of getting to attend one of those schools using a lottery research design, they reduce your standardized test scores. Okay, so this is, the idea of these choice systems goes back to Milton Friedman a little bit, right? This idea of free to choose. We want to give people choices and they can, let the market play out. So this is a very much an ongoing debate, I would say. Yeah. So I think, my takeaway right now is it should not be taken for granted that giving people choices is necessarily good for them. Now the challenging thing about that is, well, what's the alternative, right? Are there any other questions about this? Yeah, please.
You said that the opportunity to apply for Stripe GVR came from higher ranked schools.
Yeah.
So let's say if what would be the number, like the number of 0 less than, like MID being a non-degenerate number in schools that were consistently higher ranked by all applicants?
So that's a good question. I don't know the answer to that. The way people have usually asked how does demand relate to effectiveness is not through the MID, although it's a very much a valid kind of idea. What you just asked, it's a little bit more disaggregated, so they would look at some measured market share of the school and correlate that to the effectiveness of the school. So without using the true measure of demand. Mid, you could say, is a much more accurate measure of demand than other ways of computing demand, because mid is kind of what's relevant, right? That's if everyone has applied to MIT, but no one's going to get in, right? That's a very different than if people have kind of sorted themselves, and that would be kind of in the cutoff score that would be needed. So we've never done that calculation, but I think that's an interesting idea. Any other questions? Yeah.
So if you wanted to do this in a multiple type rating setting, we would simply do the simulation.
No, so you could, with lottery type breaking, one can always do the simulation. Then the onus is on you to explain how you smooth that. Okay. With multiple type breaking, the DA score formula that I showed you is a little bit more complicated. Okay, so I didn't want to go through that. Just think about multiple tie breaking as there's a product sign in front of it, because we have to think about. Yeah, so all of this kind of would work for that. This would work, say, for the Boston mechanism too. I think Irene talked about this earlier this week. I can represent deferred acceptance. I can represent the Boston mechanism or the immediate acceptance algorithm as deferred acceptance. How do I do that? I just take an applicant's preferences, and if they've listed the school first, I put them in the first priority group, right? And then if they listed it second, I put them in. So perturb that input and then run through this machinery that would all go through. So all of this would work under the DA class of mechanisms. There was one other question, yeah.
Yeah, is there any assumption about how the applicants are searching that needs to be orthogonal to the lottery itself? Because you could imagine, say there is some sort of, if like 20%, 80% will only apply for school A, 80% will only apply for school B. And then there is this small sort of intersection where they'll search for both, right? And then it's not random, it will not be randomly who will like win that lottery, right?
Right. Yeah, so what I have is a result for, fundamentally at this disaggregated school S versus not school S, right? What I showed you is kind of aggregating that up to charter versus not charter, right? So I think one way to interpret your question is maybe thinking about whether there are different estimates for people who've applied to one set of schools versus another set of schools. And so, you could disaggregate what I've showed you for, those kinds of breakouts. You're just running into data limitations and getting precise estimates there. Another way to interpret your question is to say, well, how would I use this to design a new policy, right? And that gets to the earlier conversation about we would need to think about modeling the decision to apply in addition to what's the effect of getting one of your choices. And so that would be a more elaborate model where some of the techniques we learned about earlier this week would be very relevant. Does that help?
Yeah, maybe I can also, I'm just not sure about this, right?
Yeah.
Is there some chance that you end up in some like base trap? Like there's something about if you have 80% chance of the lottery kind of people, it will be like high achievers in one and low achievers in the other, right? Then will these estimates be biased in some sense?
So, I'm interpreting this as the effect of a school offer. Now you might say charter versus not is not really what we're measuring. It's what we're measuring is you got to go to school with all highly motivated families. And I didn't, because I didn't get to go to the school that people opted for. And so you could do this technology to maybe reparameterize everything in terms of the peer mix. Actually, we just put a paper out last week doing something similar, looking at travel. So if we think about the effects of school travel or busing more generally, there's some extensions to what I just talked about that are required to study that kind of question. So all the methods could be deployed for that. You're going to run into this question, which I think is a challenging question for this literature more generally about arguing for exclusion. What I really have is causal effect of school offer. If I want to then interpret that in terms of some education production function, here I said the salient dimension is charter. You could argue, no, the salient dimension is the peer mix, right? Taking outside of this paper, the evidence that we've seen on that topic is that charter effects are largely not mediated by the peer mix at these schools. In fact, there's evidence not from Denver, but from other cities that the charters that are most effective tend to have the weakest peer groups. So it's not about you have this motivated group, weakest as judged by baseline scores. Great. Okay, let me press ahead, Nikhil. I have about 15 more minutes roughly. Yeah, okay, great. All right, so I wanted to tell you a little bit about non-lottery tie breaking, okay, because this is the second paper, and this goes back to the earlier question about regression discontinuities. And I will tell you about this in terms of a school here in Boston called the Boston Latin School. Okay, so this is a school, actually a school attended by two very famous econometricians, Chuck Mansky and Gary Chamberlain, right, are graduates of the Boston Latin School. And admissions to the Boston Latin School until very recently was based on an admissions test, okay? So let's consider two applicants to the Latin School, and how are we going to conceive about where there is some randomness in assignment? So the way I want to think about that is that randomness is going to be coming from the tiebreaker, Ri. And unlike the lottery case, where I know the tiebreaker is uniform 0, 1, I don't know the distribution of the underlying tiebreakers, okay? So let's just call that distribution denoted by F sub R for applicant I, okay? And in Boston, the way that seats are awarded to the Boston Latin School is very much like what we just talked about. BLS offers go to those who qualify. If your running variable, if your test score is less than the cutoff, then you'll get an offer at the school. Okay. So let's define tiebreaker intervals around the cutoff. Okay, so this is very much like a regression discontinuity setup. Mapping that to our kind of concepts here, I'm going to define a variable TIS of delta to be n if your tiebreaker, if your RI, your running variable, is more than delta away from the cutoff at school S. Okay, and I'll say that you're in the never seeded group there. Okay, so that's like you're far from the cutoff. If your tiebreaker is less than TS minus delta, you're always seeded. You really got in, okay? You weren't marginal. And finally, your last group are those who are conditionally seeded. Okay, so those are applicants who are in a window of size delta around the cutoff at school S. So you can basically take the same kind of setup that we had a second ago. And if we assume some smoothness in the distribution of these unknown running variable distributions, then we have an analog of the propensity score, which we call the local propensity score, and the following simple lemma. Okay, so for any pre-treatment variable WI, think about this as demographics, and applicant type theta, if I think about the limit as I shrink the bandwidth as delta goes to 0 of the expectation that Ri is less than tau s, okay, so this is getting an offer. So that conditional on your type, on your tiebreaker classification and WI, that's either going to be 0, 1, or a half. Okay, so it's 0 if I'm never seeded, right? If I shrink the bandwidth and I'm away from the cutoff, I'm not going to get an offer. It's 1 if I'm always seeded, right? If I'm way, scoring so high on the test, and it'll be exactly a half if we think about the limit as delta goes to 0. Okay, and this is just a consequence of our assumption that F is a smooth distribution. Okay, so this is going to be basically what we tell the rule. Okay. So with this in hand, we can basically do the same exact set of tricks that we just had a second ago. So if I condition not on the score, but on this local score concept, I can eliminate omitted variables bias from not only your type, what we solved in the first half of the lecture today, but also from non-random tie breaking. Okay, so this is the corollary here. If I take this limit of getting an offer, the expectation you get an offer given theta I, the value of your tiebreaker classification, and this W variable, and your local score. Okay, so this is the analog of the Rosenbaum-Rubin result. It's simply equal to the local score. Okay. So what I've basically done here is I've taken the usual regression discontinuity setup and put it in the language of our assignment mechanism. Okay. And so what's this relies on again is this smoothness of the tiebreaker distribution. Okay. Okay, so this is going to be the building block of what is to come in just a second. Okay, so now before I show you that, okay, you might wonder, okay, you're taking delta going to 0. So we're going exactly to the cutoff in this continuum model, and you're getting that the probability of assignment is exactly a half. That sounds like a fanciful scenario. Okay, that sounds like a situation of identification at infinity. Is this fact or fantasy? Okay, so I want to show you in our data that this a version of this is actually kind of playing out. And I'm going to look at New York City's Townsend Harris High School. Okay, I love this high school because Ken Arrow went to this high school. Okay, this is one of the most sought after high schools in New York. It's a test-based school. Okay, so it's not Stuyvesant, but it's one of the mainstream schools that's test-based. And what I'm going to show you is some numbers where I'm showing you qualification rates. Okay, so the probability that your tiebreaker RI is less than the cutoff, given that you are tiebreaker classification is C. Okay, so you're within the window, and I'm going to be showing this as we shrink the bandwidth. Okay, so let me explain how to read this figure. So I'm plotting on the y-axis the qualification rate. How many applicants of this type qualified for a seat at Townsend Harris? Okay, and I'm showing it for two different columns. Okay, the left column are applicants who have a W, okay, who place them in the top 25th percentile of their baseline math score distribution. Okay, so these are high achieving kids at baseline. On the right, in green are the bottom 25% baseline math, okay? Now, Townsend Harris admits students based on a test score, but also other things, okay? So, but because it's based on a test score, the baseline score here is different than that test score. But what you see is if I have a higher baseline score, I'm more likely to qualify for Townsend Harris, right? As you would expect, okay? So we have these two different types of applicants, blue and green, with different covariates, and we're looking at all applicants. Now let's take a look at what happens as I shrink the bandwidth, okay? So the first pair of columns is all applicants. I'm gonna shrink the bandwidth, and we've computed the Imbens Kalyanaraman bandwidth. I take 75% of that, I take half of that. And what you see is that in our data, we still have certain amount of thickness, okay? There's enough applicants where the qualification rate appears to converge to a half. Okay, so this abstract formulation of the regression discontinuity, there's still some data here that allows us to get some mileage here. Okay, so we were really excited to see this, and let me now press ahead. Okay, so now what do we have to do next? Okay, so I have to now deploy this technology to study what assignment risk is going to be. And what I want to do is show you how this plays out in a little bit of a simplified scenario. Okay, so we've already talked about the MID, the most informative disqualification. Okay, so I'm going to simplify our lives here and say, let's imagine we have no priorities. Okay, when we have no priorities, what happens to deferred acceptance? Well, deferred acceptance simplifies to a mechanism that we call the serial dictatorship. Okay, that's a mechanism where you put people in line, whoever's first gets their first choice, whoever's next gets their top choice among what remains, so on and so forth. Okay, and so when we have a serial dictatorship, the notation becomes a little bit simpler. I can take my formula for the MID that I had a second ago, and I only have these two cases. Okay, the first case is the MID is 0. That's no truncation. Okay, that will happen when I have no school that I prefer to school S. In any other case, the MID is simply going to be the most forgiving. Okay, that is the highest cutoff of any school that I prefer to school S. Okay, so that's what max of tau B. Tau B is the cutoff at school B for any B in my better than set. Any school B that's I like better than school S. Okay. Okay, so that's what the MID is when we have no priorities. And so if I want to tell you what is the probability of being assigned to school S with no priorities, all I have to do is ask, what is the probability that my tiebreaker variable, Ri, is in between the MID and the cutoff at school S? Okay, so if my tiebreaker is below tau S, then I've cleared the cutoff. So I would get an offer at the school, unless I get an offer at a higher ranked school. Okay, that's why we have that second term here. This term MID theta S is less than RIS. Okay, so the formula I just gave you earlier simplifies in this case with no priorities to one where I just need to govern the probability of having a tiebreaker variable in between MID and tau S. Okay, so my propensity score in this case is simply the probability that Ri is between tau S and MID. Okay, so you'd think my work here is done, right? I have now a formula for the propensity score. I can move on, but unfortunately, if I had lottery-based tie-breaking, I would be done, right? What I have here is non-lottery-based tie-breaking. Okay, so we still have a problem. I don't know what this F of R thing is, right? I don't know what the distribution of potential tiebreakers is coming from, so my mission is not accomplished. Okay. So in general, when we have non-lottery based tie-breaking, this F, the distribution of tiebreakers, is unknown, and it's an unrestricted function of theta. So even trying to estimate this is going to be quite challenging. The propensity score is going to leave the omitted variables bias from the underlying running variable uncontrolled as well. Okay, so how am I going to solve this? Well, this is where we think of the regression discontinuity. Okay, so I'm going to take shrinking windows around those cutoffs and go back to that point that I said, at exactly when delta is equal to 0, my probability is a half. Okay, but the new wrinkle here is I have these two different points at which I can think about this, right? So the usual point in the traditional regression discontinuity, when there's just one thing being assigned, would be look at a window near the cutoff, PSAT scholarship eligibility, right? The canonical application, say, I look at that window around the cutoff. That's this tau cutoff here on the right of the slide here. But I also have this mid cutoff, which is the cutoff from the higher rank rejection. Okay, so that's the new wrinkle here. And I could have someone who's got a really good test score, who's randomly assigned to the school, randomly assigned in my RD sense, by virtue of just missing the cutoff at the more preferred school. Okay, so here I have two sources of risk, just like we had a second ago. If I happen not to be in these windows, then my risk is going to be 0. Okay, so I only have risk in these two sources. Okay, and let me show you this in the data. Okay, so, oh yeah, question please.
Do we need to worry about the thresholds overlapping in that middle part?
That's a fantastic question, right? So in what we're doing here in the theory, we kind of assume that problem away. Okay, in the actual data, that can happen and does happen. Okay, so no one has thought very carefully about that. It's a great, practically important question. Usually, you know, what we've done in our empirical work is just choose the cutoff that's closest to what your score is. But it would be nice to think more carefully about that. Yeah. Okay, so let me show you some data. Okay, this is actually data not from Boston, but from Chicago. Okay, so this is data from Chicago's equivalent of the Boston Latin School. And I'm looking at applicants who have applied to the King High School. Okay, now the way to read this is I have the cutoff for King labeled here on the right, King cutoff. Okay, I'm looking at applicants who've applied to King who've also applied to a school called Brooks, okay? And these applicants like Brooks ahead of King. Okay, so an example would be someone who lists Brooks first and King second. Where would our risk be in this problem, right? So the first place you might suspect is, let's look at the cutoff for King, okay? So that's normalized here to be about 0.2324. The applicants to the right of the cutoff don't get an offer, right? So that's why the circles there are at 0. If I'm just to the left of King, I get an offer. Okay, so this is like your conventional RD here. The triangles are about enrollment. Okay, so that's thinking about take up of those offers. And I have my conventional regression discontinuity. Now I said dealing with the assignment mechanism gives us more variation to exploit. Okay, you can see that here by looking at the applicants to King who also applied to Brooks. Okay, now the Brooks cutoff, Brooks is more selective than King, is to the left of the King cutoff. It's about at 0.16. And what you see is people get offers at Brooks, okay, to the left of the King cutoff until they get to the Brooks cutoff. When you get to the left of the Brooks cutoff, you no longer get an offer at King. Why is that? You get an offer at Brooks, right? You got an offer at the higher rank choice, okay? So we have yet another experiment here around the Brooks cutoff. This is the mid for these applicants to King, okay? So we get these two experiments. In fact, what we get is a way to estimate RD effects away from the cutoff. The usual cutoff in a traditional RD study would be the King cutoff. But here I'm getting an estimate for someone who's, you know, not the last kid to get into King. He's actually the first kid to not get into Brooks, right? He's the highest scoring kid, you could say, in general, at King, okay? And so that's one of the dividends here. So I know I'm running out of time. Okay, so let me just say a couple of more things. So, you know, this is non-lottery tie breaking, no priorities. If you want to do deferred acceptance with priorities, you know, with school side constraints, there's a lot of notation. Okay, so you guys have been to a lot of notation, I suspect, on day 4 of the summer school. But the basic idea is the same. Okay, we have these experiments. The lottery case is simple. The non-lottery case, you know, the building block is this 0.5 idea. And we can deploy the building blocks of the lottery case in service of the non-lottery case by taking the limit as delta goes to 0. And this will all be fine in the non-lottery case as long as we're willing to assume that the distribution tiebreakers is smooth. Okay, so we can say that locally it's going to be a half. Okay. So the paper looks at school assignment in New York City. So New York City has lottery tie breaking. It's got multiple tie breaking, different lottery numbers, and it's got non-lottery tie breaking. So it's quite a mix. But what's really nice about this, again, is the payoff from all of these sources of variation. You can get variation due to a school-based lottery rejection or acceptance. You can get variation due to non-lottery acceptance or rejection. That's kind of the conventional things you would expect. But you can also get variation from higher ranked lottery rejection or higher ranked non-lottery rejection. Okay, so this is maybe a step towards non-local effects. Okay, so let me just wrap up here. So I didn't get a chance to talk about some applications here, but what I want you to take away is there's a lot of excitement in literature and applications and theoretical questions still remaining about how do we think about these algorithms as experiment generators? And then how can we have that information feed back into asking policy questions, counterfactual questions? Everything that I've seen on this, at least in the static case, has been focused on DA-based assignment algorithms. So something that's still not quite figured out is how to do this for linear programming type systems in a static setting. Nikhil is going to talk about some new considerations or challenges with dynamic systems. Some of the technical issues here still remain to be sorted out. So, one thing you might be asking is, didn't I say that there were about 4,000 types in Denver for 5,000 applicants? Yet I snuck by you guys that I'm taking a continuum limit approximation, right? So the continuum limit means there's an infinite number of each type, right? Yet this works, right? Why is that? Do we really understand why this works? Okay, and it's kind of the usual in econometrics, we use asymptotic arguments to try to make things work, but sometimes things just work even if those asymptotic sequences are not exactly the right sequence. And then finally, there's many other applications of this. So in education that we're pursuing. So let me stop there. I think I'm right at time. Thank you very much. Okay, we'll take a break now.